Thank you for being here as we continue our undergraduate colloquium series. Today, Dr. Chebolu is going to talk about cryptographic protocols. So in other words, his abstract promises some interesting tricks that you can try and make it look like you're reading somebody's mind, I assume. So anyhow, I'm looking forward to learning more about that. And with that, I'll introduce Dr. Chebolu.
Thank you, George, for the introduction, and thank you all for coming. So good afternoon. So this is a talk on cryptographic protocols, and as Dr. Sunil just mentioned, so I'm going to present you some interesting things. Hopefully you will learn them and you can use them to entertain your friends and family at parties. Okay, so my goal is to talk about cryptographic protocols, but it sits inside a bigger goal, and that is through academic advising. One of the common questions that I get from students and parents of prospective students is that, my son or daughter likes mathematics, really good, but what is math good for? What can they do with mathematics, So, and some students think math is very abstract and prime numbers, what good can be there for real world. So if you're the kind of person who's thinking that math is very abstract and especially number theory is very abstract and it cannot have any applications, then I should tell you that you're in good company. So do you recognize this gentleman here? Anybody in the audience? Students? This is the famous mathematician G.H. Hardy. Okay, so he's a very big mathematician. He worked primarily in number theory, among other subjects. And so this is what he said in his book, Mathematicians' Apology, written in 1940. Both Gauss and lesser mathematicians may be justified in rejoicing that there is one science, number theory at any rate, and that their own, whose very remoteness from ordinary human activities should keep it gentle and clean. So he was very proud throughout his life that he's working in number theory, a subject which is completely detached from any real-world applications whatsoever, and only time history proves that he's actually wrong. So today we have profound applications of number theory and error correction codes and cryptography and so forth. And so I think he'll be very surprised and shocked if he comes back today to realize the importance of number theory. So I'm going to talk about cryptographic protocols, but let me first tell you what is cryptography, right? So this is probably stuff that you know, but let me put a textbook definition of cryptography. So this is the practice and study of enciphering and deciphering of messages in order to render them unintelligible to all but the intended receiver. Okay? So there is some information that you want to send to someone, which is very sensitive information, and how can you encrypt that important information in a manner so that only the intended recipient can decipher and any eavesdropper who's tapping the line will not understand what it is, right? So this is the scheme. So you start with a clear text that you want to send. So you're going to encrypt that and you send an encryption. So that's the ciphertext and it's going through some channel which is not necessarily secure. Some bad guys may be tapping the line, but only the recipient on the other end can decipher the message. So that's the scheme, that's cryptography. Right? So why do we need cryptography? Well, lots of reasons you can imagine. But for a long time, it was restricted to military and government purposes. And mostly secret communication during wars and national security. So I give two famous examples in the Great World War, World War I. There was this famous Zimmermann telegram which was intercepted by the British when it was going from the German embassy to Mexico. And I think that's what triggered America into the war. And then Enigma codes in World War II generated by these Enigma machines in Nazi Germany. And that was again cracked by the British. And some historians say that that actually reduced the length of World War II by about 2 years. So therefore it's very important that you have a strong encryption to protect your data, your information that you're trying to communicate. So, and this is increasing, with time. It's kind of interesting that they say that, the First World War was a war of chemists, right? Because mustard gas was used. And World War II was a war of physicists because great physicists at Los Alamos National Laboratory, they built the atomic bomb. And it's argued that In the Third World War, if there is going to be one, I hope there is not going to be one, it's going to be a war of mathematicians, because we live in the age of data. And encryption is very important. And then it moved on to industry, in e-commerce, data mining, analytics, computer networks, server communications. So when you go on a website to browse some information, there's a padlock on the left hand, HTTPS. Hypertext Transfer Protocol with secure socket. So there's some kind of encryption that's happening there so that the thing that's communicated to the server remains secure, right? And also for privacy, emails, phone calls, online bank accounts, so forth. Not only this, but cryptography and methods of cryptography, cryptanalysis were used also in linguistics to decipher writings of ancient civilizations, right? So nobody from that time period is around to tell us what these writings are, and cryptographers, cryptanalysts, they were able to crack those things. Okay, so evolution of cryptographic methods. So I tried to put all the cryptographic methods in one slide, 2,000 years of history, just to give you the bird's eye view. So this is a result of a neck-to-neck fight between cryptographers, who are code makers, and cryptanalysts, who are code breakers, for nearly 2,000 years. It's much like virus and antivirus. There's virus which lives, which thrives until somebody comes up with an antivirus which breaks it, and then the virus gets strong, and then there's antivirus, and it evolves. The same thing with cryptography. Starting with some barbarian methods, which are really not cryptographic, but steganographic techniques, tattoos, invisible inks, and so forth. There was a time when prisoners of war, slaves were, their heads were shaved, and they would tattoo the secret message on the scalp, let the hair grow, and then, so that was the mode of communication. The other person, they have to shave their head and read the tattoos, And we come a long way from that, So next in line is some standard ciphers. Very simple ciphers, substitution ciphers, transposition ciphers, like two parties, they come up with a secret key number, and I don't know, something like 3, So every time I have a letter A, I'm going to shift it 3 units up the alphabet, so it's B, C, and D. So I'm going to replace A with a D, and then B with an E, and so forth. And such ciphers are pretty big because you can crack them very easily using frequency analysis, right? You know that in the English language, not all letters in the alphabet appear frequently. Like I think letter E and A occur more frequently than letters, I don't know, X and Z, right? So using that analysis, one can easily crack this. A little bit more sophisticated are Hill ciphers and bigger ciphers. Hill ciphers, like if you have taken a course in linear algebra, probably seen that somewhere, Basically they take a text message and the two parties, beforehand they come up with a matrix, invertible matrix. So to encrypt the message, they're going to multiply that column vector of integers with the matrix, and the person on the other end, they're going to decrypt by multiplying with the inverse transformation, right? So such were the ciphers. And then in World War II, there was this Enigma machines, looks like a typewriter, but it's very complicated wiring and motors and flippers, and so it scrambled the message in a very complex way. That was the 1940s. But the subject, I think, really took off in the 70s with the advent of computers and some important breakthroughs in theoretical computer science and mathematics. So starting with data encryption standard in 1974, and which was when the United States decided that we should create a standard, and then they wanted somebody to create a standard, and then IBM said they can make the standard. So with the consultation of NSA, that's when came the data encryption standard, which was a benchmark for encryption for a long time until 1977, when the RSA public cryptography came into place. And then the implementation of that was done in PGP, with pretty good privacy in 1991. And more recently, there's elliptic cryptography, more sophisticated one. And the current research is more towards quantum direction, right? So that's really, in a nutshell, the evolution of cryptography, starting from tattoos and invisible things, right? But really, this talk is not about encryption and decryption. That I want to go into different directions, slightly different direction on cryptographic protocols. What are these? So these are basically some interesting offshoots of cryptography which help you do some jobs which seem impossible, right? Like the ones that I mentioned in the abstract. So I put here 6, and I'd like to go through most of this. Some, in the interest of time, I will just either skip or just say very briefly. But let me start with the first one, which is the Diffie-Hellman key exchange. And before I go into the protocols, so for further reading, I recommend these two books. Actually, they're up there, but I also have the actual books here. So this is a code book by Simon Singh, which is a fantastic book. I read this over Christmas break. It's very entertaining, very engaging novel on the history of codes and breaking codes. A more technical introduction is by Neil Koblitz. It's Introduction to Number Theory and Cryptography. And I realize the importance of this, and I've done about 3 master's projects on this so far. And now I'm under the process of getting undergraduate math course in number theory and cryptography. This is under planning. So hopefully this will be offered in the near future, and students can take this course. Okay, so let's start with the big idea in all these cryptographic protocols. I think this is going to be the most important slide of my talk. So the big idea here is what's called one-way functions, or trapdoor functions. These are functions which are very, very easy to do, right? It's a function, you give an input, you get an output. That is very easy. What's hard is to go backwards. Very, very hard, extremely hard to undo. The whole cryptographic protocols business relies on the existence of such functions. Okay? I think that's the big thing that you can take from my talk. There exist functions which are very easy to do, but very hard to do. These are one-way functions. So I'll just give you simple examples. Suppose the function is color mixer, right? What it takes 2 cans of, 2 different colors, pour it, and just mix it, right? That's very easy. But if I give you the mixture, can you separate them? That's hard, right? That's the first example. The second one is the telephone directory, okay? I just got a telephone directory here, and we'll be using this version. So the input, I give you the name of a person, and the output is their telephone number. That's very easy, because everything is in alphabetical order. If I want the phone number of Cylinder, I'll just look up S, and then alphabetically I'll find George Cylinder, and I'll get his phone number. But the converse is very hard. If I just give you 309-461-8132, whose telephone number is that? There is no fast algorithm. The only thing I can do is go to page number 1, check every number, go to page number 2, check every number. So it's a function which is very hard to undo, right? But very easy to do. And then the thing that is relevant for us is multiplication. In here case, the input is going to be 2 prime numbers, P and Q. And then you have to multiply the input. That's very easy, right? But it's very hard to undo the function, right? So, especially when the primes are big. The other one is squaring mod n. I give you an integer a, and you square the integer, get a squared, and reduce it mod n. That is, find the remainder when you divide that by n. So that's a squared mod n. So these are functions which are very easy to do but hard to undo. Okay, so that's the big idea. So let's start with the protocols. The first one is the Diffie-Hellman key exchange. So it solved this long-standing problem in the field. It's called the key distribution problem. Here is the problem. How can 2 strangers exchange a secret key to start a secure communication without meeting in person? Okay? For a long time, until 1976, this was the fundamental axiom of cryptography. Any form of encryption, decryption, the 2 parties have to meet beforehand and come up with a secret key, secret matrix, whatever. Okay? Either they have to meet in person, or they have to send the secure key through a trusted third party, like a courier service or something. That was the fundamental axiom. And can we do without meeting? Okay, that was the problem. And in a seminal paper in 1976, these 2 gentlemen, Diffie and Hellman, they came up with a brilliant solution which eliminates the need to meet in person. You can do that remotely. You don't have to meet, and you don't have to rely on a secure third party. Right? It seems impossible. How can you do that, right? So the underlying idea is incredibly simple. So the way it works is, let's say I want to send something to, I don't know, Fusun, like, some gold in Fusun. So what I'm going to do, I'm going to take that gold or whatever secret information, I'm going to put it in a box, I'm going to lock it. Right? I'm going to have the key. I'm going to send the box to Fusun. Right? But when she receives it, she can't open it because she doesn't have the key. What she will do, she will put a second padlock on it. Using her own key, she will send it back to me. then I will remove my lock, send it back to her, and she's going to remove her lock. So it involves going back and forth a few times, but that's it. That is the idea. The underlying idea is deceptively simple, right? But how are you going to make this work mathematically? I mean, that's the hard work, right? So the common analogy that's given here is through paints. Obviously, in mathematics, you use numbers, and instead of multiplication, it's exponentiation. But the idea is that both parties come up with a common color, yellow. They talk publicly. If somebody listens to that, that's no problem. And then they're going to add a common color, secret color. So let's say, oops, Alice is going to add this color, Bob is going to add that color. I'm actually bad with colors, I can't tell what color that is. So some color A and color B, and then they're going to mix that, right? And they're going to transfer that, but if somebody listens to that, that's still okay. And they're both going to add back their secret color, and they're going to get a common secret. And the eavesdropper who's going through the communication that's going back and forth, he will know what this color is, the initial color yellow, and then he will see these colors, but still he cannot tell what that color is. Right? So, but mathematically the way it works is we're going to start with a group. They'll come up with a generator G for the group. Alice is going to raise to the power of A, which will be secret. Bob is going to raise it to the power of B, and they're going to swap. And Alice is going to raise it to the power of A, raise it to the power. So they get a common key, which is G to the AB. So this relies on the impossibility of solving the so-called the discrete log problem in a group. If I tell you G raised to the power of AB, I tell you G to the A, G to the B. I tell you G to the A and G to the B and G. You can come up with G to the AB, in any reasonable amount of time. So it relies on that impossibility of solving the discrete log problem. So that's how it's done. And then people try to take this one step further, right? And that is it possible to do this without exchanging the key? This is like pushing it to the max. So the goal is that any two people should be able to communicate secretly without even meeting, without even exchanging key, right? And that was solved in '77. That's the big one, the public key cryptography. So these three folks, Ron Rivest, Adi Shamir, and Leonard Edelman. So actually, they're not standing in the correct order. I think this is Rivest, Adi Shamir, Edelman. So I'm working at MIT on this problem. How can two people communicate without meeting, without sharing any secret key? So there's an interesting story that they're working on this problem. They were tired. They didn't get any ideas for a long time. So they went to a party at a graduate student's house. I think it was, what's this Jewish festival? It's Passover. And all three of them were completely drunk, right? And they went home, and I think it was Rivest who was unable to sleep because he was very tired, and then he had this math book. He was flipping through that, trying to get this one-way function which will do this job. And then he got this brilliant idea, and then he stayed up all night. By morning, he completed the paper. So the upshot is the RSA encryption. So I can't think of any other instance in the history where alcohol had such a profound effect on society. So, because the entire cybersecurity, internet security relies on RSA, right? By the way, I'm not suggesting that you guys get drunk and do mathematics. That's just history there. So here's how it works. Every person in the RSA community will have two keys. So this is called the asymmetric cryptography as opposed to symmetric cryptography, where the person encrypting and decrypting uses the same key. This is asymmetric. Every person will have two keys, right? A public key and a private key. And everybody publishes their public key. They keep their private key secret, right? Now let's say if Alice wants to send a message to Bob, what she does? She looks up the RSA directory, just like I look up a telephone directory. She finds Bob's public key, and she will encrypt using that public key of Bob. And only Bob will be able to decrypt that message because he's the only person who has the private key and no one else, right? So that's how the thing works. The idea is very simple, right? But really, how do you do that mathematically? And the math behind behind RSA is just good old Euler's theorem from 1763. See, so this theorem in pure mathematics has been sitting for 200 years, and to the best of my knowledge, it did not have any profound real-world applications besides applications within the field of mathematics. And 200 years later, these folks at MIT realized that, yeah, we can use this theorem to solve the problem of encryption, right? So if you take any integer a which is not divisible by primes p and q, then a raised to that power leaves a remainder of 1 when you divide by pq, the product pq. So then this will tell you how to generate the keys e and d. You just pick two integers whose product is congruent to 1 mod phi n. By the way, n is just the product pq. Phi n is the Euler's function, which is this quantity in the exponent. Then integers less than n that are co-prime to n. Doing that is easy. You create an algorithm which runs in polynomial time will generate those keys. That's no problem. So E is going to be your public key and D is going to be your private key. And this is the encryption and decryption. So Alice wants to send a message M. She's going to look up Bob's encryption key, that's E. So she's going to raise it to the power of E. And when Bob receives that message, he's going to decrypt. So he's going to raise it to the power of D. In view of this identity, in conjunction with the Euler's theorem, the result is back to N. So that is how the RSA encryption works. Okay, so it's very simple when we give it to you, right? But the hard thing is to come up with such thing. So here I'm ignoring the implementation issues. I'm just working on the theoretical side of it because this is at the intersection of theoretical computer science and math. So we have to look at time complexities and there are other issues there that I'm cautiously hiding under the rug, but just the abstract mathematical idea is pretty simple, right? Okay, so this RSA actually pushed its way into digital signatures. And so authentication. To prove that the message was created and sent by a known sender. I receive an email, let's say, from George Sillinger. How can I know that George composed that email, right? So that's authentication. Integrity, the message was not altered in the transit, right? So that's very important. And non-repudiation, the sender cannot deny having sent the message. So it's like a fingerprint, right? How do you do all this mathematically? And these are all interesting offshoots of the RSA encryption that I just talked about, where you combine the private and public keys of two parties in clever ways to accomplish these jobs, right? So you should read Coblett's book for more details, you know. So in the interest of time, I'm going to move on to other things, but that is one way in which the RSA encryption has been helpful. Okay, the next thing I want to touch base briefly is the oblivious transfers, you know, which is a very big topic, but I'm going to just mention one problem. It's called the Yab's millionaires problem. So the question is that how can two millionaires, in this case Steve and Bill, figure out which of them is richer without revealing their actual wealth? For a long, long time, this problem people thought was impossible to solve, right? And you can imagine other instances where you can use this, right? In the abstract, I mentioned one thing, right? Like, how can you figure out whether your friend received a better grade than you on the final exam, right? You know? So you can't go up to them and say, how much did you get on the final? You know, you can't ask them at the same time. You're not comfortable revealing your grade. So there is a brilliant protocol, which is a result of Andrew Yao, a Chinese computer scientist, came up in 1982. So there's a protocol, and you go through the protocol, and at the end, you will determine the inequality between the two people. But neither party will have any clue of what the other person actually has or made. You know? So that is an important problem in cryptography, and it has applications in e-commerce and data mining. You know? So this is one problem, but this fits into a bigger class of problems called oblivious transfer, where transfer goes, information gets transferred from one end to another end, and parties will not know which information is being transferred, or selective information is kept secret, right? Also used in cloud computing too. Okay, so that is another very interesting problem, and several years back, one of my graduate students, he did his master's project in which he analyzed this. And more recently, when I taught Math 410 to graduate students, they actually went through this protocol, and they actually did this in class. So they took the last 4 digits of their student ID numbers, and they figured out which one is bigger, and that's less confidential, right? So they went through the protocol, and they were able to determine that. So it's quite amazing thing. The next one, again, the offshoots of the RSA is the zero knowledge proofs. Okay? So this actually came up in graph theory, right? So it's a cryptographic protocol by which one party can prove to another party that a given statement is true without conveying any information other than the fact that the given statement is true. So it's like really finding Hamiltonian paths and graph coloring, right? So how can I prove that I found a Hamiltonian cycle without showing you the actual cycle or something? Right? And there will be lots of other cases where you can use this. For example, the one I gave you in the abstract. Suppose there's a very, very hard Sudoku puzzle, right? And Bob, he's unable to solve the puzzle. But Alice was able to crack it, right? The question is that how can Alice prove to Bob that she has solved the puzzle without showing him her solution, right? Of course, showing the solution is one method, but she doesn't want to do that because then maybe Bob is a bad guy, he's going to take that solution and then claim ownership on that, and he's going to show the people that I have solved it, right? So she doesn't want to show the solution, but she wants to prove without any doubt that she actually solved it, right? So there is a brilliant protocol for this one. It's a probabilistic zero-knowledge proof. So let me explain how this works. So here's a puzzle, right? You all know Sudoku, right? It's a 9 by 9 grid. The only condition is that you should place with the numbers 1 through 9 every row, every column, and every 3 by 3 submatrix or whatever grid should get the numbers 1 to 9 exactly once, right? That's the puzzle, and Bob is unable to solve, but Alice has solved it. And here is the solution that Alice came up with. So this is the given puzzle, and this is her solution. Okay? Now, she has to prove to Bob that she has proved it without giving the solution. What she's going to do is she's going to come up with a permutation. She's going to fix a random permutation of the digits 1 to 9. So 1 goes to 5, 2 goes to 9, 3 goes to 4, etc. So that's just a permutation of the numbers 1 to 9. What she does, she permutes the entire puzzle, right? So the left-hand side is the original puzzle solution, and this is the permuted solution. For example, 7 should go to 6, so there you go. 7 is replaced with 6. 8 should go to 7, so there is 7, and so on, right? So that is the first step in the protocol, right? So Alice picks a random permutation of the digits 1 to 9, and she applies that permutation to her solution, right? Now she commits to that solution, and there's a cryptographic way in which that can be done. So there's a padlock through, again coming from RS encryption, she can lock all the digits. So once she commits, that's it, she has to step up. She cannot touch that anymore, right? Then Bob has the following options. Bob will ask Alice to reveal only one of the following. Not in the original puzzle, but the permuted puzzle, right? Either he can ask to reveal a row of his choice, a column of his choice, a 3 by 3 submatrix of his choice, or the permuted Sudoku puzzle. Only one he has to do it, right? And then she's going to show just, let's say, show me the third column. So everything will be closed, just the third column will be revealed. So then Bob, after Alice reveals one of the above items which Bob requests, Bob is going to check the Sudoku condition. That is all the digits 1 through 9 appear or not. Okay? Note that when he does that, he will not know anything about the original problem because this is uniform distribution on the permutations, right? So it's picking at random, and all the digits 1 through 9 will appear. That will shed no light on the solution to the original problem whatsoever, right? But Alice could be cheating, right? So suppose if the original puzzle had no solution, or Alice doesn't know how to solve the puzzle, she was just bluffing, right? Bob will catch Alice with a probability of at least 1 over 28, right? So there is here, so 9 from each of these, 9 rows, 9 columns, 9 sub-by-sub matrices, and then 1, 27 plus 1, 28. Equivalently, Alice is successfully cheating with at most 27 or 28 probability, right? Simple computations, probability computations, right? So how is this good? Well, then you iterate this many, many times, right? So first, oh, maybe she's lucky, do it again. Oh, maybe she really knows it. And then your confidence builds, right? And when you repeat the protocol 150 times, Alice's chance of cheating in all 100 rounds is at most 27 over 28 to the power of 150, which is less than 0.5%, right? And you can actually decrease that even further by repeated applications. So this is a probabilistic zero-knowledge proof, right? So at the end of the protocol, Bob will be pretty darn convinced that Alice has solved the puzzle, the Sudoku puzzle, but he will have no clue on the solution to the original problem, right? So this is what is done, actually was done originally in the graph coloring problem. So there is a graph, want to show that it's three colorable, and yes, there exists a zero knowledge proof that you can prove that to someone that yes, I colored the graph with three vertices, but the person will have no idea what the actual coloring is, you know. And the Sudoku puzzle can be reduced to the graph coloring problem. Okay, so that is Sudoku, and hopefully you can use that when you solve, next time you solve a Sudoku puzzle and you want to show someone that you proved it without revealing your solution. Right? Okay, now comes the last section of my talk. This is coin tossing over the telephone. Right? So I think this is the thing I want to spend the remaining time. So coin tossing over the telephone. So the question is, how can you toss a coin over the telephone? But I put it in a problem. So let's say Alice and Bob are getting a divorce. Okay, so they're a couple. They're getting a divorce, and so as you can see, they are not happy. They're yelling at each other, and so they're separated, and they're discussing on the telephone who gets what. Right. So I guess that's what people do when they get a divorce, and but they don't seem to agree on one thing. Right. So, and that is who gets the car. It gets very, very, very interesting actually. So that's a very nice car. Who would not want to have such a nice car, right? So so they decide, and after a while, they decide, okay, let's do a coin toss to figure out who gets the car. But then they realize there's a problem. Oh, we are in different places. How can we toss a coin over the phone? And flipping a coin over the telephone is tricky, right? Because especially when the people don't trust each other, right? And you don't want to bring a third party as a referee, so you want to deal it between the two of you. How are you going to toss a coin over the telephone, right? So that is the problem. How can Alice and Bob, who live in different cities and don't trust each other, flip a coin over the telephone without bringing in a third party, that's a referee? And again, this is, I'm saying flipping a coin, but this is a random experiment, which similar to coin tossing, which will have two equally likely outcomes and no party can cheat. So technically it's a Bernoulli random variable with p equals 1/2, right? So that's what we are looking for. And there is one easy solution to that, and that comes from the telephone directory function that I told you, right? It's a function, very easy, hard to undo. So here is a simple protocol. Let's imagine that Alice and Bob, who are separated, living in different places, have identical copy of a telephone directory, right? So, and let's assume that there are equal number of people in the interval a to m and n to z. So a number of people whose last name begins with a to m is equal to the number of people with the last names n to z. So let's assign these to be heads, those to be tails. Very simple. So here's the protocol. Alice picks a telephone number at random from this directory and tells it to Bob. That's like tossing a coin, right? And Bob now has to guess whether the name corresponding to that telephone comes from the first half of the book or the second half of the book. And remember, that's a very hard problem, right? You know, you can't search, right? So the best you can do is to make a blind guess, 50-50, right? If Bob guesses it correctly, he will win the car. Otherwise, Alice gets the car, right? And this is a protocol in which no party can cheat because they both have the same telephone directory.